Hello, I am Achintya Haldar from the University of Arizona. I'll be talking to you on intelligent structural design using functional materials in civil engineering. I have been working on it from the very early part of my career, and I'm going to share with you some of my work in the past 4-5 decades. I'm going to talk about motivation, commonly used materials in civil engineering, advantages and disadvantages, and then a few intelligent design options. And I'll finish my talk by making some concluding remarks. Materials used in civil engineering are brick and masonry. They used over centuries, but not very widely at present. Concrete, it is used all over the world. Steel, where available, it is used. It has many desirable properties, including ductile behavior, is yet to construct. Wood, it is used mostly in the US for residential building. It is prone to damage by moisture, fire, termite. Also, since we have to cut down trees, it is bad for environment. We use glass for non-structural nature in most cases. We started using composite material, carbon fiber with resin. I will talk very briefly about it, then soil and soil pile system. Now, when we talk about new material, what we are looking for, new material can be stronger, cheaper, easy to work with, better appearance, and present recent technological advancement. In most civil engineering applications, available materials are relatively cheap, at least in the US, but the labor cost could be very high. At present, developing new materials is an important research area. Developing new material can be expensive. Sometimes cost of energy required to produce them can be more than the available material. In many ways, for most material, we must have ASTM standard. Right now, people have started using carbon fiber with resin, but we do not have the ASTM standard for resin, and that is a major drawback, and that limits its application potential. Recently, I attended a conference, and one lady talked about there are 3 resin manufacturers in Brazil, and nobody knows what they are made of. Now, I would like to make this proposition. Instead of developing new materials, can we use available materials in intelligent ways, producing more economical and improved desirable structures expected from new material? Now, some of the things we talked about or we studied are eccentricity in connection, strategic use of steel frames with concrete shear walls, flexibility in connection, post-mortise connection, strategic use of different material, soil and pile. Let's take each one of them one by one. When I talk about eccentricity in the connection, you can see I'm not giving this bracing number to the connection. There is always some kind of eccentricity. Now, there's a new paper I just read in June 2023, just last month in ASC Structural Division Journal, and you can see how they are proposing to make the connection eccentric. I cannot go too much in detail into it, but you can look at it at your own time. Now, the advantage is concentric fully western connection can be very expensive, several $1,000s in the US. Eccentric connection may reduce the loads in the main member, and that way the structure can be more economical. Now, before I go forward, I want to compare different design alternatives. All of us, we know what is load and resistance factor design concept or performance-based design concept. These are reliability-based design. One of the major advantages of risk-based design is that different design can be compared by estimating their underlying risk. Risk is always estimated in terms of reliability index beta, and the probability of failure can be calculated as 1 minus phi of beta. Phi is the cumulative distribution function of standard normal variate. Beta between 3 and 4 values are very common in civil engineering application. Higher beta values are always better. It gives us low probability of failure. In civil engineering application, we are looking for probability of failure of the order of 10 to the power minus 4, 10 to the power minus 5 in that particular range. I'm going to talk about a first different strategic use, how we can use different material. I design a frame and you find that when I apply the lateral load, it is very weak. To make the lateral, increase the lateral strength, I put then concrete shear wall, and I'm going to give you the result. Material properties I'm giving you here, and probability of failure without shear wall. For this particular frame, I made it really so that it would fail is 100% probability of failure. When I verified it with Monte Carlo simulation, it is 1. It is basically giving me the good result. But when I put the shear wall, that risk has gone down to about 10 to the power minus 3, and both reliability method and the Monte Carlo method works. So here I'm showing if I use different material intelligently, I can get the behavior I'm looking for. Now, when I was in Georgia Tech, I used to teach there. They built IBM Tower. It is a 50-story high building built in about 1987. This concept was used. Basically, the stair wall and elevator shaft block was used as concrete shear wall. They used laser-guided slip-form concrete in about a week with extremely accurate result. Within a week, it got very good result. And then steel frames were attached to that, providing the stability is looking for, lateral strength it is looking for, and steel frame can be built 3-4 at a time. So that means overall, it would give us economic design. In US, flexibility of the connection is very important. We have 2 types of flexible connection, type 1, type 2, and type 3. Type 1 is fully rigid, type 3 is partially rigid, and type 2 is rigidity is between 1 and 2. Here I'm showing the result. This one, the dotted line here, chain dotted line, it is basically fully restrained connection. This line with solid line, it is partially restrained connection. And in this case, the chain dotted, it is the stiffness is between this fully restrained and a pin connection. And when I take those connections and try to calculate probability of failure, I found that this is the FR, fully restrained connection, reliability index for serviceability and strength for curve 1, curve 2, and curve 3. You can see none of them are similar. Even for when I use very flexible connection for serviceability, the risk could be more than 50%. And you can see FR and curve 1, we use it for the same purpose, but you can see FR are giving me higher reliability index or lower probability of failure, so it is not conservative design. With that, let me talk about flexibility in connection post Northridge connection. Now, peer connection possesses a quantifiable and non-moment capacity intermediating degrees between the rigidity of type 1 and type 3. Experimental studies suggest that all connections for steel structures are flexible with different degrees of rigidity. The implication is any analysis technique used will require nonlinear algorithm. Linear techniques such as moment distribution method, slope deflection method we teach to undergraduate cannot be used. So these are more computationally more complicated. Now, during the Northridge earthquakes of 1994, connection fractured in more than 200 steel buildings. And 5 years ago, during the Northridge earthquake, similar cracks were developed, but they were undetected over 5 years. This is the typical pre-Northridge earthquakes. I'm going to call it bolted welded flange. And you can see this bottom flange, this part fractured in a brittle manner, causing those fracture mania. Now, following the Northridge earthquakes, American Institute of Steel Construction immediately recommended not to use it anymore. It generated a considerable amount of research interest in the profession. Attempts were made to make the steel connection more flexible. Now, many connections were developed. I cannot talk about it. I'm just going to identify some of them. Cover-plated, spliced beam, slide-plated, bottom haunch, connection with vertical ribs, reduced beam section or dot bone, or slotted holes in the weld. I'll talk more detail in this particular presentation. Here I'm showing a typical dot bone arrangement. You can see the beam flanges are reduced at the top and bottom. Also, we can use twisted strand people use. In post-Northridge earthquakes, I call it BWDF with added ductility. One of my colleagues, Professor Ralph Richard, developed it, and this connection was patented. All he did, he cut notches, very small, about quarter-inch wide notch at the top and bottom of the web of the beams. And many people thought cutting notches would make the frame more unstable, weak. But experiment shows that actually it is not such that. And many times when we have this moment flexible connection, we express it by moment rotation curve or in theta curve, and we can use that in theta curve in many different ways. I have seen people use linear, bilinear, piecewise linear, polynomial, exponential, cubic B-spline, and Richard model with 4 parameters, and I used it in my work. This is the 4 parameter. I am showing it here. They would look like this, and initial stiffness K, plastic stiffness Kp, reference moment M naught, and curve shape parameter N. Dr. Richard developed a computer program. For a given connection detail, it will give you the 4 parameter you're looking for. So they basically proved that their method, their connections are not going to make the frame weaker. So they actually did some full-scale testing, and they shared the data with me. And I am going to show you the result. You can see pre-Northridge connection, dotted connection with the same number, and when we built it with post-Northridge connection, initial slope of this curve in theta curve remained the same, but it is much, much stronger. We think they did it for loading part, but seismic loading or dynamic loading, we need to have a reloading, unloading part, and we use meshing rule to develop the hysteretic loop. And we then calculated for those test result, those 4 parameters of the Richard curve, and then we took a frame and a 2-story frame, a small frame, so that we can verify use Monte Carlo simulation, excited it by dynamic loading, and I am going to give you the reliability index. You can see the reliability index in many cases for serviceability is negative. means it is almost sure it is going to fail. Probability of failure is more than 50%. For strength, some of them are relatively good, but not as good as we want. So what we did, we took another 3-story frame and we put all those member where we did the experiment, Professor Richard did the experiment, and these are the member they use. And then I'm going to give you the 4 parameter of the Richard model with pre-Northridge connection, and then for other 4 parameter with post-Northridge connection. And look what happened. I calculated the probability of failure for reliability, for serviceability and strength. And you can see what happened. If you assume they are FR type, fully restrained, probability of failure is 10 to the power minus 3, same as post-Northridge earthquakes. That means it did not reduce the strength. But if we use pre-Northridge earthquakes without the slotted hole, you can see probability of failure is about 12 times higher. So after that, we added some shear wall just to show it is the bottom 2 floor. And this is the only 1 floor. And again, when we calculated the probability of failure, you can see pre-Northridge earthquakes, when I talked about it in figure 5, when we have 2 floors, it is of that order of 10 to the power minus 6. It improved, but when we use only 1 story shear wall, it went up. The probability of failure is 10 to the power minus 3 now, but you can see how we can here put different technologies to obtain the result we are looking for. Now, some of you may know me as a structural engineer, but I wrote my PhD thesis on liquefaction of sand. The liquefaction means a structure sitting on the top of it. It is not going to do it. The soil is moved from the bottom of the foundation and it will tilt and you can come out. During 1964, Niigata earthquakes in Japan and Alaska earthquake in US, they had tremendous amount of liquefaction problem. Now, most of the basic concept is when you apply total pressure, some of it goes to intergranular contact called effective stress and pore water pressure. When during earthquake, sometimes this effective stress tends to 0 and pore water pressure becomes total pressure, and basically soil acts as a liquid, and that is why structure tilts. Many nuclear power plants are located close to the large water bodies, really, and they need to be checked for liquefaction potential. What are the different reasons we can use? We can, option you have, we can replace loose sand. In most cases, it may not be practical. Install rock drain, sand depot compaction, dewatering, freezing the site. I know one site was permanently frozen, a combination of other alternatives. Now, what happened here? Here I'm showing a saturated sand deposit. This is going to start to flow away, and we are going to provide piles to stream in this. Now, after in 1992, for Niigata earthquake, they excavated the site, and here they said how pile was damaged. We took that and tried to analyze it in many different ways. Obviously, in this case, we took piles and we developed a finite element model and tried to find out the strength of this pile. So let me talk, I cannot go too much into detail. Let me make some concluding remarks. Intelligent structural design using available materials is essential for efficient, economical, and practical design of structures. Various methods and techniques are being proposed. They can be analytically challenging due to enormous advancement in computational power. These new analysis and design concepts need to be used. Intelligent design can fill the knowledge gap by utilizing desirable features of available material. Now, some of you know I work in risk and reliability areas. These are the books, other books I published. These are published by John Wiley. They're widely available. This left-hand side book is published just in March of this year. Very new. If you want to know how to calculate risk, you can look at it in more detail. Thank you for listening to me. This is the campus where I am from. Thank you.